All right, everyone. Welcome to this lecture. And we are waiting a few minutes in order to our friends are going to join us. It's good to have you here tonight, and I'm honored. Let's wait a few more minutes, and then we begin. All right, thank you very much, Ms. Eftekhari. And as I said earlier, I'm honored to have you all in here in my lecture, and I hope it's going to be useful for you since it's a new field in science and it's very detailed science. I try to make my lecture understandable. So in order to make it more understandable, I made my lecture in notes uh, in order to uh, be much more understandable and to avoid misunderstanding. So we are going to begin our lecture, and so welcome everyone. Today we are going to an exciting journey into the field of astrobiology. This field of science seeks to understand the potential for life beyond Earth and the conditions that support it. We will explore what astrobiology encompasses, its significance, and the methods scientists use in their search for extraterrestrial life. And I'm trying to go slowly for our friends to better understand. So here it comes, our very first question. What is astrobiology? I think the very first question that we're going to answer is this question, and we shall say astrobiology is a new field that merges various scientific disciplines, including biology, chemistry, astronomy, and planetary science. At its core, astrobiology is concerned with the question of life in the universe. It examines the origin of life on Earth and how life evolved and the potential for life to exist elsewhere in the cosmos. So, research in astrobiology comprises these three main areas: the study of habitable environments in the solar system and beyond, the search for planetary biosignatures of past or present extraterrestrial life, and the study of the origin and early evolution of life on Earth. So, um, this this kind of field seeks more questions, and some after this concept that I explained, these questions rises from it. So astrobiology helps us answer profound questions such as, are we alone in the universe? What are conditions allow life to thrive? And how did life begin on Earth? So there are also other questions such as, how did life begin at the first place? What are these? What are the essential ingredients for life? How does life adapt to extreme environments? And what might extraterrestrial life look like? So, astrobiology also considers the future of life, both on Earth and in the universe. As we venture into space and explore other planets, understanding the conditions that foster life will be crucial for our survival and exploration. So why is astrobiology so important in these days? One of the essential questions that thrives from this was the first question. It addresses some of humanity's most profound questions regarding our existence. Are we alone in the universe? Finding extraterrestrial life would have profound implications for philosophy, religion, and science. Uh, By studying life in extreme environments on Earth, we can gain insights into the resilience and adaptability of life. This knowledge can inform us about the potential for life in harsh conditions elsewhere, such as on Mars or the icy moons of Jupiter and Saturn, and as well as some other planets outer our solar system. So the pursuit of astrobiology drives technological innovation. The tools and techniques developed for space exploration often have applications on Earth, leading to advancement in fields like medicine, environmental monitoring, and material science. Astrobiology fosters collaboration among scientists from different fields, encouraging a holistic approach to understanding life and the universe. This interdisciplinary enhances our knowledge and promotes innovative solutions to complex problems. So, these are the main reasons that why astrobiology is important these days, and I think in few decades, few further decades, this importance it's going to become much more than this because of many reasons. One of the reasons can be needs of resources. We can harness many raw material from mediators, from stones that are just circling around in the space. And in few decades, we are going to be so serious on that concept. So we are going further, and we want to talk about the search for extraterrestrial life, which is one of the most important aspects in astrobiology, and we are going to go a little deep into this. So here in this slide, we have telescopic observations, planetary missions, and astrobiological field studies, as well as SETI Space Telescope and upcoming technologies, sample returns missions that we are going to explain shortly for you. So the quest to discover extraterrestrial life involves multiple approaches with various methods, technologies, and scientific factors. Um, Key aspects of this research include these topics that I told you earlier. So we're going to have a little explanation for each of these. So telescopic observations. It can be both exoplanet discovery or spectroscopy. Using telescope like Kepler Space Telescope and TESS, uh, referring to transiting exoplanet survey satellites, known as TESS, to identify exoplanets in the habitable zone of their stars. And in the case of spectroscopy, analyzing the light from distant planets to detect chemical signatures in their atmospheres that could indicate the presence of life, such as oxygen, methane, or water vapor. So, with spectroscopy, we can detect elements in atmospheric in the atmosphere of each planet that we can just detect. So it's gonna be a great step for our knowledge to use such methods. And in case of planetary missions, robotic landers and rovers, missions like NASA's Perseverance on Mars and the European Space Agency's Rosalind Franklin rover are designed to search for signs of past or present life through analysis of soil and rocks in other planets, such as Mars. Icy Moons missions, like upcoming missions to Europa. Europa is a Jupiter moon, which has an icy surface, and beneath it there is an ocean with a depth of hundreds of kilometers. So icy moons missions are so important for our knowledge, and as well as Enceladus. Enceladus is a Saturn moon, and in Enceladus we will explore surface oceans to identify conditions which can support life. So in upcoming missions, we are going to beneath the Enceladus surface. Astrobiological field studies. Studying extremophiles in Earth's harsh environments, such as hydrothermal vents or polar ice caps, to understand the limits of life and inform our criteria for habitability elsewhere. And analog missions, which conducting simulations in extreme environments on Earth that mimic Martian or alien conditions to prepare future missions and improve life detection strategies. And As we continue on the topic of search of extraterrestrial life, we going on SETI. SETI, which known for search for extraterrestrial intelligence, which includes radio signal monitoring, utilizing large radio telescope to listen for potential signals from intelligent civilizations. Projects like Breakthrough Listen aim to scan the sky for narrow radio signals that may indicate technological life. So we are every day, every hour, trying to detect any sign of radio signals from outer space, which has a origin of extraterrestrial life, and it still goes on. And in the aspect of optical SETI, searching for laser emissions as, as a means of communication from advanced civilization, leveraging both ground-based and space-based telescopes. So we also observing things, observing stars, observing any sign, any just abnormal sign that we could just confirm that it belongs to extraterrestrial life. So these two aspects are also very important. And another issue is space telescope and upcoming technologies, such as James Webb Telescope and Hubble Space Telescope, as you can see in the picture. You can see the Hubble Space Telescope. And James Webb Telescope has launched in December 2021, and it's designed to study the atmospheres of exoplanets and detect potential biosignatures through advanced infrared observations for the first time. So it's going to be a huge step in our science having James Webb Space Telescope. Actually, I'm very happy that I'm living uh, in this state, and I can see uh, many results of James Webb Telescope, which is very interesting, and you can see many planets that are like our own Earth, and it's more than maybe 3,000 planets that it has been detected, which are like our planets in many ways. So we're gonna talk about this topic uh, in the further lectures. I'm gonna pass it now. And further missions like Large UV Optical IR Surveyor and HABEX, known as Habitable Exoplanet Observatory, aim to perform detailed surveys of exoplanets in search of life. And so these are upcoming missions. I hope they're gonna achieve this. And sample return missions, such as Mars Sample Return Mission, planned missions to collect and return Martian soil and rock samples to Earth for detailed analysis, which could provide definitive evidence of past life, and also asteroid and comet sample returns. Missions like Osiris, which known as returning samples from the asteroid Bennu, explore the building blocks of life and the materials that may have seeded life on Earth. So there is a hypothesis. There is a hypothesis these days that scientists are talking about, and they say that there could be a chance that the very beginning of life on Earth has been originated in early meteors in our solar system. And this hypothesis can be approved or unapproved only based on the by, by those returning samples from the asteroid. So these are very important missions as well. And we're going to pass this page. And interdisciplinary collaboration, which bringing together experts from various fields such as microbiology, planetary science, chemistry, and engineering to create comprehensive strategies for detecting life, and collaborating with space agencies around the world to pool resources and expertise in the search for extraterrestrial life. Public engagement and citizen science. Engaging the public through citizen science projects such as a galaxy zoo, where individuals contribute to data classification, creating a wider network of participation in the search. And about philosophical and ethical considerations, we can say that considering the philosophical implications of discovering extraterrestrial life, including its impact on religion, culture, and our understanding of humanity. Ensuring that the search for life does not contaminate other environments and that potential extraterrestrial life is treated ethically and with respect. This is the matter that we might uh, have facing with it with creatures like animals these days, animal rights, and these subjects are referring to such things that even extraterrestrial life has rights if we discover them. So, and we passed this topic, and it has been shortly explained. So we are going to our next topic, which is conditions for life in the space mostly. For beginning of every life, there are some conditions are required, and the best conditions that we know about it is the conditions that has been applied on our Earth. So we gain our knowledge based on the study of life in our own planet. So the most important one is the liquid water. It's so essential for sustaining life. Water facilities, bio, biochemical reactions, serving as a medium for metabolic processes. It dissolves essential minerals and nutrients needed for biological functions. So understanding the essential conditions for life is critical in the search for extraterrestrial existence. This approach examines various factors necessary for life, such as liquid water, as we discussed about, and such as chemical elements, which essential elements uh, like carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur are crucial for forming organic molecules. So chemical compounds are very important in this topic, and the presence of prebiotic molecules such as amino acids is necessary for life's foundational processes. So after existence of water and organic compounds, the necessity of its reactions and the reactions that those molecules are going to have in the liquid place are going to result in molecules and more how do I say, much more complex molecules like amino acids and DNA and proteins, and the life is going to be much more complicated after this. So life might utilize alternative biochemistries, for example, silicon-based life, under different environmental conditions. So there are possibilities that because of silicon atom features in chemistry, it could be a substitution for a carbon molecule, carbon atom in the molecules. So it could be a completely different life uh, type, silicon-based life, we say, because the future of this atom is so similar to each other. And in case of energy sources, we have three aspects, like solar energy, chemosynthesis, and diverse energy utilization. Solar energy, like photosynthesis, utilize sunlight to convert light into chemical energy, primarily in plants and algae on Earth. And chemosynthesis life in extreme environments like hydrothermal vents relies on chemical energy from minerals instead of sunlight. And organisms can adapt to use multiple energy sources, making the environments and their inhabit more diverse. So another aspect that is so important in sustaining life is a stable environment. A stable, such as a stable temperature. A stable temperature range allows for the presence of liquid water and the possibility of life. Also, active geological processes help maintain nutrition cycle, allowing ecosystems to thrive. A stable environment, aided by a strong atmosphere, can protect life forms from harmful cosmic and solar radiation, as we have it in our Earth, and like ozone layer, for example. And it can be categorized under atmospheric condition as well. Atmospheric conditions is like rich in essential gases like oxygen for respiration, carbon dioxide for photosynthesis, supports various life forms. So life forms by using oxygen and carbon dioxide can just uh, run their mechanism in order to sustain their life on our planet. We have to find very similar situations in other planets as well. So a thick atmosphere can burn up meteors, preventing them from reaching the surface and causing mass extinction events, such as our own. We have a thick atmosphere that prevents many asteroid impacts. And a suitable atmosphere helps maintaining stable temperatures, crucial for biochemical processes. On the other hand, pH and chemical stability is one of the other important things for sustaining life. And life on Earth thrives in near neutral pH conditions, around 6 to 8 pH, which is conducive to biological reactions. Stability, stability in the chemical environment allows for the formation and maintenance of complex organic molecules. Changes in pH from natural disasters like volcanic eruptions can influence local ecosystems and potential affect habitability. So natural disaster like volcanic eruptions can change pH of the ecosystem, uh, and as well as one of our big extinction in story of life in our planet. Uh, it was during, I think, before the dinosaurs that there was a volcanic eruption on Earth that extinct up to 75% of all life on Earth. And this is one of the main reasons. So, time and evolution ability. Life requires billions of years to evolve, stable conditions to support the development of complex organisms, drives environmental conditions, promote speciation through ecological niches and evolutionary pressures. And geological timescales provide evidence of past life and the conditions that once supported it, critical for understanding potential life elsewhere, like fossils record. And next aspect is planetary systems considerations, which one of them is star type and habitable zone. The type of a star significantly influences the potential for life. The habitable zone, known as Goldilocks zone, is crucial for maintaining liquid water. A plant's orbits also must be stable enough to prevent drastic climate change that could affect habitability over time. Moons can impact a plant's climate and may provide additional sites for potential habitability. For example, Titan, which is a moon of Saturn, and extremophiles as a model. Extremophiles demonstrate that life can thrive in extreme conditions, such as extreme temperatures and pressures. Studying extremophiles contributes to our understanding of potential habitats on other planets like Mars or Europa. Research on extremophiles reveals unique biochemical pathways that could inform the search for alternative forms of life. So, we are going to open this topic a little bit for you, topic of extremophiles, because it's very important in astrobiology. Extremophiles are organisms that thrive in conditions that would be inhospitable to most life forms. Studying these organisms expands our understanding of life's adaptability and informs the search for extraterrestrial life. Some notable examples include uh, thermophiles, halophiles, acidophiles, and alkalinophiles, and special case tardigrades that we're going to discuss about. About thermophiles, as you can see in the slide, these heat-loving microorganisms can survive in temperatures exceeding 100 degrees Celsius, such as those found in hydrothermal vents on the ocean floor. Their ability to withstand extreme heat suggests that life could exist in similar environments on other planets. In case of halophiles, or halophiles, better say, sorry if I'm pronouncing wrongly, these salt-loving organisms thrive in highly salinity environments. Such salinity environment is an environment full of salt, which we have one of those environments in Iran named Gamsar, salt mountains of Gamsar. You can visit. It's kind of a high salinity environment, such as salt flats and salt mines. Their unique adaptations enables them to survive in conditions that would dehydrate most life forms. So any other life forms that going to these places are going to dehydrate, except those who are halophiles. Another case is acidophiles and alkalinophiles. These organisms thrive in extremely acidic or alkaline environments. Respectively, studying their metabolic processes can reveal how life might survive on planets with harsh chemical conditions. Extremophiles serve as model for potential extraterrestrial life forms, showing us that life can adapt to a wide range of environments. And our special case is tardigrades, which is one of my favorites because in the recent experiments that they have been done in the United States, um, they send tardigrades in the vacuum of space on under the non-pressure and UV rays. Tardigrades could survive over 10 days, and this is one of the very special cases in our nature for survival, which is very interesting. Tardigrades can survive catastrophic events like volcanic activities or um, me- meteor impacts or ocean flows. They can survive every kind of apocalypse. So they are one of the most important. They are one of the most important creatures in our planet. And we are going to next slide, which is conditions for life. No, it's the previous one. Sorry, it was the previous slide. We're going to next slide. We can see a tardigrade. I put just a picture of it for you that you can see such a tough creature. Earth has been created and it can be easily moved by any meteor to other planets and maybe start a new life form in other planets or moons. It's really a representative for our life that can provide it for other harsh conditions and environments in our solar system. So we are going to pass this and exoplanets and the habitable zone. The search for habitable exoplanets is one of the most exciting frontiers in astrobiology, as it opens up the possibility of discovering life beyond our solar system. The discovery of exoplanets and planets outside our solar system has transformed our understanding of where life might exist. Key concepts include the habitable zone, Kepler and TESS missions, and characterizing exoplanets. The habitable zone, often referred to as the Goldilocks zone, is the region around the star where temperatures are just right for liquid water to exist. Planets within this zone have the potential to support life as we know it. Every star, whether it's small or big, depends on its temperature, has its own habitable zone. NASA's Kepler's mission has identified thousands of exoplanets, many of which reside in their star's habitable zone. The Transiting Exoplanet Survey Satellite, known as TESS, continues this work, searching for nearby exoplanets that could be studied in greater detail. Scientists use various methods to characterize exoplanets, including transit photometry and radial velocity measurements. By studying the atmospheres of these planets, researchers hope to identify biosignature that could indicate the presence of life. So we're going to next slide. The role of astrobiology in future explorations, which I'm going to go faster in this topic in order to avoid you to get boring. If there is any questions, I'm ready to hear it from you. Let me see. Is there any questions up till now? Okay. So we shall continue with this topic. Astrobiology plays a crucial role in shaping future exploration missions. Some key aspects include these key aspects that you can see. I'm going to pass on one by one for you. Mars missions. Mars has long been a focus for astrobiologists due to its potential for past life. Missions are equipped with advanced tools to search for signs of an ancient microbial life and collect samples for future return to Earth. Icy moons explorations. The icy moons of Jupiter, known as Europa, and Saturn, known as Enceladus, are prime targets for astrobiological research. Both moons are believed to have subsurface oceans beneath their icy crust, creating environments that may harbor life. Future missions such as NASA's Europa Clipper aim to investigate these moons in detail. Recent studies suggest that Venus may have had conditions suitable for life in the past. The detection of phosphorine in its atmosphere has sparked interest in exploring this planet's future. Missions to Venus could provide insights into its geology and atmospheric processes, enhancing our understanding of planetary habitability. Missions targeting asteroids and comets, such as NASA's Orisis, as I explained earlier, and Japan's missions named Hayabusa 2, are important for understanding the building blocks of life. These bodies may contain organic molecules that offer clues about the origin of life on Earth. Interstellar missions. Although technically challenging missions aim at studying exoplanets and even interstellar objects could reveal new insights about the life beyond our solar system and the diversity of planetary environments. Project focusing on returning samples from various terrestrial bodies like Mars and Moon and asteroids are crucial. These samples allow scientists to conduct detailed analysis in laboratories on Earth, enhancing our understanding of potential biosignatures. Developing new technologies for space explorations, including autonomous robotic systems and advanced sensing instruments, is essential. These innovations expand our capacity to explore and understand distant worlds and their conditions for habitability. So this is one of the most important topic as well, technological innovations, because every day it's going to upgrade our knowledge, our limitations for explorations, such as AI. AI is one of the uh, most crucial ones. Collaboration with other disciplines. Astrobiology encourages collaboration with fields like geology, chemistry, and planetary science, allowing interdisciplinary efforts in understanding life's potential in the universe. joint efforts can lead to comprehensive approaches to studying extraterrestrial environments. And public engagement and education that inspiring public interest in astrobiology is vital for garnering support for exploration missions. Outreach and educational programs can excite future generations about the space science and the search for life. International cooperations are important as well. Collaborative missions among countries can enhance the scope and success of astrobiological research. Shared goals in the search for life can foster diplomatic relations and promote peaceful cooperation in the exploration of space. It can lead to a faster approach for scientifics. By highlighting these additional aspects, the presentation illustrates the multiple role that astrobiology plays in future exploration efforts. Feel free to modify or elaborate on any points as needed. Okay, so technological challenges in astrobiology. So we are going to look at some challenges, especially in technological aspect in astrobiology. As you know, astrobiology relies on advanced technology for research and exploration, raising these several challenges. Spacecraft design, sample returns missions, remote sensing limitations, and raw material limitations. Designing spacecraft that can survive and operate in extreme conditions is a key challenge for astrobiologists. Missions to planets or moons with harsh environments requires innovative engaging to protect instruments and personnel. So this is one of the most important challenges because we are going to protect our human assets as well as our materials and the operation itself. In case of sample return missions, collecting and returning samples from other celestial bodies like Mars and asteroids presents logistical challenges, including the need for robust sterilization technique to prevent contamination. So in order to avoid any contamination by uh, other bacteria and viruses that we are going to provide to that environment, we have to sterilize our samples, and after those protocols, we are going to return them to Earth. In the case of remote sensing limitations, detection of biosignatures from distant exoplanets is complex. The technology to study these atmospheres is still developing, and interpreting data accurately requires sophisticated models. So we are still working on it. And about raw material limitations, in order to achieve best performances in our operation and systems, we need costly materials such as gold, silver, and diamonds, which makes the process quite hard and costly. So these were some of our limitations in the field of astrobiology. Some of the most important ones that we have bolden here. And the next issue is the Fermi paradox, which is an issue that becomes one of the main arguments between scientific societies. So the Fermi paradox questions why, given the vast number of stars and potentially habitable planets in the universe, we have not yet detected evidence of extraterrestrial life. Some proposed explanations include rare Earth hypothesis, the conditions that make Earth sustainable for life may be exceedingly rare. Factors such as a stable sun, a large moon, and the right distance from our stars could be unique to Earth. Technological maturity. Advanced civilizations may self-destruct before achieving interstellar communications or travel capabilities, raising questions about the longevity of intelligent societies. And the great filter, which this concept suggests there may be a critical step in the evolution of intelligent life that is incredibly unlikely. Either life seldom evolves to intelligence, or intelligent civilization often self-destroy. That we can open these topics in our lectures in Parallel School in the future for you. And I'm going to just point some other aspects and then discuss about Kardashev scales, which is one of the most interesting topics in astrobiology for you. And then we're going to end our webinar. Um, so we are going to continue with ethical considerations. As we explore the cosmos in search of extraterrestrial life, we must consider the ethical implications of our actions. One of them is finding life. If we discover extraterrestrial life, how should we respond? This question raises ethical considerations about the potential impacts on both the discovered life and our own civilization. Should we attempt to communicate, or would that pose risk to both parties? And about planetary protection is to avoid contaminating other worlds with Earth microbes. We must adhere to strict planetary protection protocols. This involves sterilizing spacecraft and carefully planning missions to minimize the risk of contamination. How we communicate discoveries of extraterrestrial life is crucial with public communication. So, misinformation or sensationalism can lead to public panic or misunderstanding. Scientists must strive to communicate findings accurately and responsibility, fostering public interest while maintaining scientific integrity. These ethical considerations are essential as we move forward in our exploration of the universe. Interdisciplinary connections, such as philosophy, environmental science, and astrophysics, which we are going to pass quickly. Astrobiology links with various fields. One of them is philosophy. Questions about the nature of life and our place in the universe lead to philosophical discussions on existence, consciousness, and the meaning of life. As we study extreme environments on Earth, we gather critical data that can inform conservation efforts and our understanding of climate change. And knowledge about planetary formation, stellar evolution, and the distribution of life supporting planets enhances our ability to search for habitable worlds. Is the main issue of astrophysics issues. So the future of astrobiology, one of the main topics, as you know, as you hear every day these days in your life, is AI. AI technologies can analyze vast amounts of data from space missions, searching for patterns that include the presence of life. Machine learning algorithms are increasingly being adopted in astrobiological research. And synthetic biology, which can be reachable in near future, investigating how synthetic organisms could survive on other planets, can provide insights into the potential for life. This emerging era can also lead to innovations that may help us adapt our biology for space travel. And in case of collaboration with private sector, we can say increasing involvements of private companies in space exploration can expand, such as uh, space. Uh, I forgot the name of company of Tesla. Um, Sorry, because of my memory. And okay, let's go back to the topic. Increasing involvement of private companies in space exploration can expand research possibilities and funding opportunities for astrobiology, leading to innovative missions and technologies. SpaceX was the name of that company, sorry, that private sector. For example, SpaceX is going to invest in this field for next 50 years or something, or maybe 100 years. Because governmental sectors are limited for budgets, but private sectors are much more um, able to provide such budget for these missions. As we pass these argues, we're going to our last topic, which is one of my favorites. It's the Kardashev scale. Kardashev scale um, is method developed by Russian astrophysicist named Nikolai Kardashev in 1964. It categorized it categorized civilizations based on their energy consumptions and technological capabilities. This scale helps us conceptualize the potential development of intelligent life forms and their ability to harness energy from various sources. So, we are going to talk about type 1 civilization, which known as a planetary civilization. A type 1 civilization can utilize all the available energy on its home planet. This includes all forms of energy, such as solar, wind, geothermal, and fossil fuel. Approximately 10 to the power of 16 watts or 10 terawatts, which represents the total energy produced and consumed by humanity today. If we want to put our recent civilization in this topic, we're going to give a number of 0.75. So we are not still type 1 civilization. We are 0.75. There are there are still way to go in order to reach that civilization. So achieving type 1 status would require global cooperation, significant advances in energy and technological advances, and the sustainable management of resources. Civilization would need to capitalize on the renewable sources while trans, trans, transiting away from fossil fuels. We should go one more step and avoiding to use fossil fuels to reach that type of civilization. So in type 2 civilization, known as stellar civilization, a type 2 civilization can harness the total energy output of its star. This could be achieved using a construction like a Dyson sphere. Dyson sphere is kind of a construction that this kind of civilization going to build around its own stars in order to harness a total amount of energy of its stars. So about 10 to the power of 26 watts, equivalent to the energy output of typical star like our sun. Such a civilization would have advanced engineering skills, enabling them to manipulate vast amount of energy and conduct large-scale projects involving astronomical structures, such as Dyson sphere, that has been proposed by Dyson. Type 3 civilization, known as galactic civilization. A type 3 civilization can access and utilize the energy of an entire galaxy, tapping into billions of stars and their planetary systems. So in type 3 civilization, the situation is completely different. There are many stars that are going to be harnessed. Approximately 10 to the power of 36 watts it's going to consume this kind of civilization. And this civilization would process immense technological capabilities, including advanced space travel, interstellar exploration, and manipulation of galactic scale phenomena. They would have harnessed energy from supernova, black holes, and other cosmic processes. So they don't look forward to use any kind of energy from their stars. They're going to use energy from black holes, from supernovas, because for reaching this amount, I mean 10 to the power of 36 watts, the energy come from stars are not enough. So they have to change their methods for harnessing energies. And if we go further in Kardashev scales, we have two more type of civilizations. Type 4 civilization, known as universal civilization, a hypothetical civilization that controls energy at the scale of the entire universe, manipulating dark energy and other fundamental forces. So the black holes and other cosmic processors are not enough for this kind of civilization. They're going to harness the dark energy itself in order to sustain their civilization. So it's very interesting. And finally, type V civilizations. Actually, it's not finally, but in Kardashev scale, it's the final one, which is type 5 civilization, known as known as multiversal civilization. So this kind of civilization is going outer the universe itself, a theoretical civilization that could access and utilize energy across multiple universes, transcending known physical laws It means that they are able to change physical laws for themselves. So it's so mind-blowing. And beyond this type, we used to call that civilization omega civilization. Beyond type 5 civilization, any kind of civilization that exists are called omega civilization. That we don't know anything about it. It's just kind of a hypothesis. So this was it, and that's all. Thank you for your attention. Thank you for your time. I really appreciate it. In conclusion, we can say astrobiology is a dynamic and interdisciplinary field that seeks to answer fundamental questions about life in the universe. By studying the organisms and evolution of life on Earth, we can better understand the conditions that support life elsewhere. As we continue to explore our solar system and beyond, we are on the brink of potentially groundbreaking discoveries. Whether we find evidence of microbial life on Mars, explore the surface oceans of Europa, or detect biosignature in the atmospheres of distant exoplanets, exoplanets, astrobiology will play a pivotal role in expanding our understanding of life and our place in the cosmos. So that was all for today, and thank you for your attention. And I look forward to our discussion in the future. If there is any question about these topics, I'm ready to answer. And if there is not, then I'm giving my regards to you, and I hope you all be fine. And thank you again. So, Mrs. Iftikhari, I'm going to finish my lecture here.
Thank you
No,
so much for.
it was an honor. It was an honor to have you.
Thank you very much, Dr. It was so great.
It was an honor, Dr. Jalili. In the presence of you, I cannot say anything more. So, uh, my best regards to all of you, and I hope we're going to have more lectures about astrobiology, because I know it's a topic that you're all love. So God blesses you all. Thank you.